The next speaker is Bhupal Dev, who is Bhupal has a PhD in particle physics from the University of Maryland and did postdoctoral work in the UK and Germany before joining the faculty of Washington University. His research specialization is beyond the standard model of particle physics and cosmology. He has published over 100 peer-reviewed international journal papers, that's really awesome, on related topics, and is currently working on the anomalies of the cosmic microwave background and the implications for the evolution of the universe. So without further ado, I will let Bhupal take the show away.
Thank you, Joe. Can everyone hear me in the Zoom?
Yes.
Okay, great. Okay, so let me just put my slide over here, share, and make it full screen. So how do I make it only showing one screen there?
Use slideshow.
Use slideshow?
Yeah.
Well, I mean, I don't see the other screen also. That's fine. Doesn't matter. Okay. Okay, yeah, so thank you everyone. Hare Krishna. So I'd like to thank the organizers, Brahmatirtha Prabhu, Krishna Mataji, Doc Prabhu, Leela Mataji, Sthitadi Prabhu, and everybody involved for putting together this wonderful conference. It's my first time visiting BI and attending this BI conference. And I'm new to BI. I've been attending some of these monthly sessions maybe for the last few months, and I've learned a lot in this time. So I'm really excited to be within your Sangha and trying to learn things and also trying to contribute whatever little I can. So when Dr. Prabhu asked me to give a talk on my research, I was thinking like, what can I really present, which will be of interest to the BI community. And I was reading through some literature, and then I found this very interesting topic, which I thought would be relevant for the discussion here. So this is some research that I'm still doing. It's not published yet, and I'm still waiting for more data to confirm this. But yeah, I would like all of your input in this regard. Okay, so let's get started. So this is the outline of my talk. I'll talk about, first I'll discuss about this Brahmanda, cosmic egg concept from scriptures, and giving some references from scriptures that how the universe is described as in the shape of an egg. And then I'll present some recent cosmological evidence for this concept, and mostly coming from cosmic microwave background. There have been some discussions of this already in this conference. I'll go a little bit in deeper and trying to dissect what the CMB data really tell us, and why there are some issues with the CMB data and how that can be addressed by invoking this egg set or spheroidal, the ellipsoidal universe. In particular, I'll talk about this anomaly called the quadruple anomaly. I'll explain what that means, and why that requires you to have a non-zero eccentricity rather than just a pure spherical symmetry for the universe. And then if I have time, I'll touch upon this another very interesting tension called the Hubble tension, measuring the value of the Hubble constant by two different methods. They don't agree with each other at the moment, and this idea also can help us resolving that Hubble tension. So let's see how far we can go. So just if in case some of you fall asleep during my talks, I'll just give the punchline from the beginning that there is a growing cosmological evidence which confirms the scriptural view of an egg-shaped universe. That's kind of the take-home message from this talk. Okay, so let's go into deeper. So first I'll start with some Vedic quotes, and this is some Vedic evidence. And one of the last Zoom meetings, Advaita Prabhu was very particular that you have to separate Vedic from Puranic. So I have been careful here. First talk about the Vedic evidence, then I'll talk about some Puranic evidence. So this is straight coming from Rig Veda. The reference is right there. It's a very famous verse in Rig Veda. Let me just put this a little bit aside. Yeah, this verse says, Hiranya Garbha Samabarta Tagre Bhutasya Jatah Patir Ek Asit Sa Dadhara Prithivim Vyam Udemam Kasmai Devaya Habisha Vidhema. So the most important word in this verse is Hiranyagarbha. And Hiranyagarbha, I guess all of you are familiar with this term. And this the literal translation of this sukta is saying that Hiranyagarbha was present at the beginning. He was the sole lord of created beings, and he upheld this earth and heaven. Let's offer worship with an oblation to the divine. So what does Hiranyagarbha mean? Hiranya means gold, and Garbha means embryo. So Hiranyagarbha represents he who was in the golden egg as an embryo. And here is a picture of a golden egg found from Google. This basically refers to Lord Vishnu, right? He's referred to as Hiranyagarbha. And this same verse in a slightly different context also has been referenced in Taittiriya Samhita. Here is another reference. Those were scholarly in the scriptures. Maybe you'll like to know that and maybe dig deeper into that. So there are also numerous other references to this concept in the scriptures. And so I'll give just 2 or 3 Puranic evidence, and then I'll move on. I'll just to make my point clear. So in the Srimad Bhagavatam, there are several places where this concept of this, this golden egg or Hiranyagarbha has been described. I'll just give 2 examples. There are other examples mentioned yesterday in Bhavaneshwar Prabhu's talk, for instance. So this is in the second canto, 5th chapter, 35th verse. It says, Sa eva purushas tasmat andam nirvidya nirgataha sahasro angri bahoksho sahasranana sirsavan. So it says the translation, the Lord Mahavishnu, although lying in the causal ocean, came out of it and dividing himself as Hiranyagarbha. That's the translation by Srila Prabhupada. Hiranyagarbha, he entered into each universe and assumed the Virat Rupa with thousands of legs, arms, mouths, etc. So this andam again is referring to the cosmic egg. There is another verse that's coming in the 3rd canto, 26th chapter, 52nd. This is a big verse. I just took part of it. Etad andam visheshaksham, which says that this universal egg, or the universe in the shape of an egg, is called the manifestation of material energy. So again, this reference to the cosmic egg comes there. Okay. And then in the Brahma Samhita, there is this famous verse, 535, Ekopi asura chaitum jagadanda kotim yat saktir asti jagadanda chaya yadantaha andantarastha paramanu chayantarastam govindamadi purusham tamaham bhajami. So again, so this term jagad anda, it appears 2 times, and then this anda also is appearing again. So there's numerous references to this cosmic egg. So the question is that why the universe is referred to as in the form of an egg shape, right? Anda means egg. Brahmanda means the cosmic egg. There are many more references. I'm not going into all the details of that. My point is that so how we we can try to understand this from the modern cosmological point of view. That's the point of my talk. Before I go into that, I'll just show you this nice painting. I took this from a drawing by Gauranga Sundar Prabhu. Maybe he took it from somewhere else, I don't know, but I just took it from his blog. This shows the Mahavishnu lying in the causal ocean, all the universe is coming out from his pores, and then he's just zooming into one universe here, which has these 14 planetary systems, the lotus stem and everything here. But you see that this nice, you have this egg-shaped universe here. So this is showing this very nicely in this picture. So I just thought that's interesting, just for the visual representation. Okay, so now let me move on and see what is the modern cosmological view on the shape of the universe. Okay, so that's the thing, that's the main theme of my talk today. Okay, so how do we know about the shape of the universe? What kind of observables we can we can study in order to find the shape of the universe? Because we just have this one universe, we can't get out of our universe to study it, because when you talk about shape of an object, you look at the object from outside, right? And then you know the shape of an object. Like you hold a ball, and if you're inside the ball, you probably can't tell what shape of the ball is. Like if you put an ant or something inside it, you probably can't tell the whole shape, but you have to go outside to get the view. So, but we are inside the universe, so we can't get out and see what the universe looks like. So how do we really know how to how we get the view of this universe? So So the modern cosmology, it was basically initially some something just some theoretical mathematical stuff, blah blah. But then until people had this real experimental data coming from cosmic microwave background, that's the beginning of the era of precision cosmology. And this started with an accidental discovery. In 1964, these two gentlemen up there, Penzias and Wilson, they were working at the Bell Labs in New Jersey, and they had an antenna, this one behind here, and they're trying to measure some radio waves. Okay, and this was during the Cold War times. They wanted to spy on the Russians and so on, so they wanted to pick up some radio signals from some satellites, I mean, some echoes and some satellite echoes. And they tried to remove, so they wanted to make this instrument very sensitive so that they can pick out signals from, from Russians or whatever. And so they tried to remove all possible backgrounds, and still they were always getting this kind of faint noise. It's like a background noise, consistent. It was, and they tried to remove it, they could not by all means. And in fact, they even went up to this antenna, they found some pigeon holes there, some pigeon nests. So they tried to remove that and so on. Still, they could not get rid of this background. So, yeah, so, and then they talked to their colleagues at Princeton. Princeton is close by. They talked to some cosmologists there, some theoretical people, and they found that around the same time there was a very interesting theoretical paper by Robert Dicke, Jim Peebles, and others. So here is a picture of Jim Peebles here, who got the Nobel Prize last year, along with Roger Penrose, or maybe the year after. I forgot. I don't exactly remember. Anyway, so yeah, so. They basically they showed the results to them, and they immediately found that this is something of very interesting. I mean, this is of something of important consequence. They immediately realized that this could be coming. This is not something, some artificial noise. This is just coming from the Big Bang. So that's when they found that, okay, they have made a really big discovery. They published the papers back to back, the theory paper first, and then the experimental paper in Astrophysical Journal Letters, and then the rest is history. These guys got Nobel Prize and so on. So that's when this precision cosmology really started, with this discovery of the CMB. So the question is, what exactly is CMB and why it is so important, right? So here is a picture. I'll try to explain. This talk will get a little bit technical. Please forgive me for that. I'll try my best to explain it in as simple language as possible. So here is the picture of the universe as it evolves. This is the Big Bang. Okay, so the universe is believed to have started some time ago, and so it has a certain temperature that time. This is written in Kelvins here, and this is the time since the Big Bang started. So the time starts really from this very small amount called the Planck time, because before that, with known physics can explain what happens before that. All the laws of physics will break down after this, before this time. Then you go to this, what is called the singularity. So we'll start the time from there, 10 to minus 43 seconds. And then the temperature that time was 10 to 32 Kelvin, is pretty hot. And the energy was, translate that, it becomes 10 to 19 GeV. GeV is a unit called giga electron volt. Electron volt is basically the amount of voltage you need to accelerate an electron through the potential difference of 1 volt, and that's basically gives you the unit of energy. It's like 1 eV is like roughly 10 to minus 19 joules, if you want to know in terms of the SI units. Okay, and then what happens? So just after the Big Bang, so it's not like the universe was in a kind of tiny point and the rest was empty. So the whole space was basically that much size. Okay, so there's nothing existing outside of that space. The space itself was tiny. This is kind of difficult to imagine, but this is how we should understand the Big Bang. Not like it just happened at a point in space and the rest of the space was empty. Not like that. The whole space was that size. And then it went through expansion, just to explain why the different points in the universe as we see today are causally connected. So there is an idea to explain that, which is called inflation, that in the beginning, just if it expands at a constant rate, that is not enough to explain why the different parts of the universe are causally connected at the moment, because light can only travel at a certain speed. And if you take the size of the universe today, then it's not possible for the 2 points on the extreme ends to be causally connected. But the universe looks kind of isotropic and homogeneous on a pretty large scale. And to explain that, there's this idea of inflation. There's an exponential expansion of the space-time itself. So if there's an exponential expansion, then that can explain why the different points can be causally connected. Okay, and so but this has to end at some point, and after that, the universe, kind of it expands at a constant at a constant rate. And then after some time, again, it will have some accelerated rate and so on. So the point is that once the inflation ends, which is happening, it's like very short time, right? -43 to -35 seconds. And then all the particles are produced at the end of inflation. There's a particle called inflaton that decays and produces all the particles. It's called reheating. And then all these particles are in kind of a soup, in a cosmic soup. So it's a primordial plasma, and the light which comes from the Big Bang itself, it cannot really penetrate through this because the light interacts with charged particles, and all these charged particles are right there. So the light just interacts with them and it cannot escape from there. So it's like, so they're all kind of trapped inside. And then at some point when the universe expands and cools further, then you produce all these neutral atoms. The electrons, the proton becomes, the electron goes around the proton, becomes a hydrogen atom, then they become helium atom and so on. You just build up the periodic table. And so once you have the neutral particles, then the photon can no longer, scatter so efficiently with neutral particles. It only scatters against the charged particles, right? And so then the photon can escape. And that's basically what we see today is the cosmic micro background. So you go through all these different phases here, and then roughly around this, around 3,000 years of age, that's when you have only the neutral atoms, then the photon starts escaping. And then when the first stars and galaxies form, that's roughly 300,000 years. And so the light we see today that's the relic coming from that long ago. Okay, so when the universe was just some 300,000 years old, and that's the cosmic micro background. Okay, I hope it makes sense to everyone. And now, so that time the temperature was pretty large again, 3,000 Kelvin. But now, because again the universe has expanded further and further, so today we have only 2.7 Kelvin. Okay, as the temperature. Okay. So it is a small cartoon just showing that picture that initially when you have only charged particles in the soup, then the photons cannot escape. They just scatter against these charged particles and get trapped inside. The mean free path is very small. But after some time, when you form the neutral atoms, then most of that space is empty. The nucleus is only in a tiny place inside the atom, and then the electrons are surrounding, rotating about it. So the photons can now just escape through. And that's where you see these kind of little blue signals, they're kind of going out. So this is the CMB basically. It's coming from this surface, which is called the surface of last scattering. That's when you have the neutral atoms formed. So that's the CMB basically. So since I probably can do a better job than the professional astronomers did here, trying to explain this in a video. So I'll just play this video. It's by European Space Agency that shows this picture. So I got really motivated by Doc Prabhu's nice presentation yesterday to show some videos. So here is one. Let's see if it plays. And I can put some. Okay, so I'll just switch off the volume. But you can just see the picture here. It's trying to show exactly how the satellite which measures this CMB, how it does it. It's a Planck satellite, which is at 1.5 million kilometers away from the Earth, and it rotates, and then around. As it goes around the Earth, and then the whole solar system is moving around the galaxy. So it just maps out the entire universe. Okay. And this is how, so they have 9 frequencies to remove what I call the foreground emissions from the galactic center. And then they just, get this very precise map of the early universe. Okay. So they detect, the places of the star formation in the galaxy. And then they use this molecular gas to trace the star formation across the galaxy. And they also discover many new galaxies in the universe. This is going beyond even the Hubble Space Telescope, because this has a much deeper field of view, because it's tracing things all the way from 380,000 years to today. And so it gives us a very nice picture of how all these stars and galaxies and galaxy clusters form in the early universe. So you see all these beautiful pictures. These are the cosmic filaments. So all these little dots, they're actually galaxy clusters. It's called cosmic wave. You see these different galaxy clusters there. And so this is a cosmic wave. And if you just extend it backwards, you just make a slab out of it. So you have this 380,000 years ago that the Big Bang, the CMB picture, and then you're looking forward, and then you see all the structure formation and how the light really gets transformed when it goes through all these structures through gravitational lensing and so on. And from there you can tell about the history of the structure formation. So this is basically the first ever the whole sky map, which is that much accurate. I'll talk about this picture later, what all these little dots tell. But but this is basically what are the outcome of this analysis. And this is a some $1 billion project. Okay, so and what comes out of that is this map. Okay. They also have some hints of these anomalies, which I'll talk about later. But this is basically the picture. Okay. Sorry, I have some noise. Okay, okay, good. So let's move on and try to understand what exactly is that map about. Okay, so first of all, why the temperature is so small? Why is it so cold now? Okay, out in the universe. So that has to do with something called the black body radiation. So here is this is the spectrum. The x-axis is the wavelength, or you can translate into frequency. They're related by just the speed of light. And then on the y-axis is the relative intensity of this of the signal. Okay, and so there's a peak here, you can see, and then you have this kind of spectrum. This is a typical of what is called a black body spectrum. And what a black body is nothing but just something you put an object, you put an heated object in a black room, and then it emits radiation. And that's basically that. The spectrum will look like this. That's basically black body radiation. An isolated object which is emitting radiation. That's basically black body radiation. Okay. And it has this characteristic peak, and that peak temperature right now is this 2.7 Kelvin, and then it has this spread. Okay. And so you can understand that from this formula, and how this peak temperature is related, how the peak frequency is related to the temperature. Here, that's called the Wien's law. In those who know thermodynamics know that very well. So they're inversely proportional to each other. So if you decrease the temperature, then this peak lambda will increase. Okay, and this constant is called Wien's constant. Its value is this 2.8 times 10⁻³ meters times Kelvin. Okay, so from there you can actually translate where that peak temperature, the temperature will correspond to what lambda or what frequency. The frequency is just a C of lambda. And so it corresponds to millimeter wavelength, or about 100 gigahertz frequency. So that's why it's called microwave, because gigahertz is the microwave frequency range.
Prabhu, when you move away from the microphone, you're difficult to hear.
Okay, so I should just stay here and try to. No, that's fine. I'll just stay here. Okay, thank you, Prabhu. Okay, and why is it so cold? So in the at the time of when the CMB was first emitted, this 380,000 years ago, the universe was only 3,000 Kelvin, and now it is only 3 Kelvin, and the reason is that the universe is expanding, right? So all these waves, they're also being stretched, and as they stretch, their wavelength increases, right? Or their frequency decreases. And that's how you get to this temperature, because the universe expands, it cools down, and you get to this temperature of 3 Kelvin, 14 billion years ago, which is now. That explains why it's so cold. Okay, so now let me try to get into the details of how exactly, what does this map tell us? This map is so important. So what are exactly telling us? All this different color coding here, that is basically telling you the temperature fluctuations about this mean temperature we saw, this 2.7 Kelvin, right? And so this color coding here is the blue means it's below the mean temperature, and red means it's above the mean temperature. So the cold and hot spots. Okay, So this red means it's a hot spot and blue means it's a cold spot. And as you can see from this picture, it looks roughly uniformly distributed. There is no like kind of a preference for a particular part to be hot or a particular part to be cold. It's kind of randomly distributed. And that's the signature of this CMB. And that basically, so this temperature fluctuations comes because of some quantum fluctuations in the early universe. And that is a prediction of the inflationary model actually, that you would get this small fluctuation here and there, and just out of vacuum, you'll get this fluctuation. And that's what actually is the seed for producing all the structure. So all the structure that we see today, including ourselves, that cannot exist without this fluctuation. Because if there is no, everything was uniform, there you will not form any structure. So you need to have this fluctuation so that there's pockets of larger density, pockets of smaller density. The ones that are larger density, gravity starts working on that, and then tries to bring them together more and more, and that forms eventually stars, galaxies, and everything. So these are very crucial for the existence of all the structure that we see today. Okay. Yeah, so that's one thing. And here is just a picture showing how the precision improved. In the 90s, there was the first satellite called Kobe. They mapped the CMB, and that it looked like this. And then came 10 years later WMAP, which it measures with more precision. You can see that the resolution increased quite a bit. And now again, after 10 more years, Planck came and it gives us this picture. So you see how over the last 20-30 years, the picture has evolved. Okay, so now they're getting this, measuring these fluctuations with higher and higher accuracy. Okay, and maybe after 10 more years, it will be even more precise. Okay, and the question is what we learn from this. Okay, what we get, investing billions of dollars in trying to make this more and more precise. So that's the next part. But before I go in there, just because the title of my talk was evidence for X-shaped universe. So let me just make a first clarification that just because this picture looks X-shaped, it is not really, X-shaped. You cannot tell from here whether it's egg or not. And that's simply because of this geometrical fact that, you are mapping something three-dimensional, and you're trying to put that into a screen, which is two-dimensional. So how do you do that? This is very similar to what we do, when you do a map of the world, right? A globe. A globe is three-dimensional, or it's three-dimensional. But when you try to project it onto a map, which will hang on the wall or whatever, then you put it in 2 dimensions, right? How do you do that? So there are particular types of projections. This name is called ITER projection. They can also do this called Mollowite projection and all other types. But this is one particular type of projection. So you preserve the most of the features without distorting, except that the poles will be distorted significantly in this way, right? Because in the 3-dimensional picture, the pole is just a point, but now when you translate into 2 dimensions, this gets stretched, right? So like Antarctica is now all over the place here, but yeah, the rest of the world looks similar. So and we don't care so much about Antarctica, so it just everything is fine. So same thing happens for this picture of this Planck, right? I mean, this is a picture of WMAP, but you can get the same idea, right? So what the satellites do, what it does, it just maps the whole sky and it puts a 3D picture. But then if you want to present it, then you have to put it in a 2D picture, right? Now preserving all the features, all the correlations and everything. And the way you do that is exactly the way you take a map from 3D to 2D. So that's what they do, and that's why you see it kind of this form. But this does not necessarily mean that it is it's in an X-shaped or something. But the question is this really spherical, or there is something more to that? And that's the point that I'm going to talk about. Okay. So just by looking at this picture, we cannot tell what is exactly the shape, because this looks is consistent with spherical. Okay, so to do that, I'm sorry, I have to go a little bit into the mathematics here, but this will be one of the very few questions I have. So I promise. So this is called multiple expansion. So what it does, so you write this temperature, you're trying to measure the fluctuations of the temperature about some base value, right? So what you do, you expand this temperature in series of some terms. This is called this multiple expansion. Okay, so you have this these YLMs are called the spherical. They're called the spherical harmonics. They're functions of these 2 angles, theta and phi. One is the the polar angle, one is the azimuthal angle, and then you have all these coefficients ALM. So they basically tell you what particular multiple is in what amount in this temperature fluctuation, and then you just sum over all these L's and M's. L is similar to like orbital angular momentum, and M is this value takes from minus L to plus L. It takes two L plus 1 values basically. Okay. So here, just, I mean, this kind of difficult to probably understand. So I'll just put a picture here. So L equal to 0 will be like, it's called a monopole. So means that it's all uniform, right? You just have one uniform temperature. So that's the monopole, L equal to 0. And then if you go to L equal to 1, that's called a dipole. And there you have three different values, because M can take value from minus L to plus L. So if L equal to 1, M has to be integer. So it has to be -1, 0, or +1. So -1 is this one, 0, M is -1, M is 0, M is 1. But in all cases, you see you have two poles, right? And like there's one kind of a hot part of the, half of the part is hot and half of the part is cold, right? These two different color codings. So you basically get a dipole. By dipole, you mean that you have two different poles. One is hot, one is cold. Or in case of the charge, you have like a positive charge, a negative charge, and so on, right? So that's basically the dipole contribution. And then you go to higher poles, like L equal to 2 is called a quadrupole. Okay, there you have 5 different values for M, -2, -1, 0, 1, and 2. And then if you go to L equal to 3, that's called octupole. There you have 7 different values, -3 to +3, then L equal to 4, and so on. You can go to infinite number of L's like this. Okay, and as you go higher and higher L's, you see that the picture, it gets prettier and prettier. You get all these different structures now. And now the map you saw in the previous slide, that's a superposition of all these different poles. That's why it's called the multipole, right? Multiple expansion. You get superposition of all of these together. And that's how the map, they get this small, the dots, the cold spots and hot spot, and so on. Okay. Yeah, so if you apply this to CMB, this L equal to 0 would correspond to the monopole, which has this mean temperature, 2.7 Kelvin, with some error bars. And then the L equal to 1 is the dipole, and there's anisotropy, dipole anisotropy, which, as you see, it's pretty small. It's like a factor of 1,000 smaller from the monopole, right? So these are tiny fluctuations. It's not big. And then you go to the next one, quadrupole, you see the flux is even further smaller. It's like microkelvin, 10 to -6, like million times smaller than the monopole contribution. So these are tiny fluctuations you're trying to measure, okay, in the temperature. But these are significant, okay? Without them, no structure can form. Now this dipole one is easier to understand, because we know that the sun is moving around the galaxy. And so when the satellite is up in the sky, so the satellite is moving around the Earth is moving around the sun. So there is what is called the Doppler effect, right? So when you are moving, if the light that is coming towards you, if you're moving in the direction of the light, then you see the frequency, to be higher. But when you're moving away from it, then you see the frequency to be lower. That's called the Doppler effect, right? And you can get this experience even when like an ambulance passes by. You hear when ambulance approaches you, you hear the sound gets louder, and then it goes past. Then you find the sound kind of fades, right, and becomes smaller and smaller. So it's the same thing. It's called Doppler effect, right? The change of frequency because of the relative motion. So that explains the dipole anisotropy. But there is nothing really that can explain this quadrupole anisotropy, okay, which is then the higher mode, L equals to 2 mode. And that's what is related to the shape of the universe that I'll talk at the end. And then for L equal to 3 and 4, now these are very higher modes, and the anisotropies get smaller and smaller, and the Planck does not have that much sensitivity to find smaller ones. Like their resolution is only like microkelvin, so they cannot go beyond that. But there could be also something hiding there in the higher multiples. Maybe some future instrument will pick it up. Okay, so what comes out of that map is what is called this multiple picture. So on the x-axis is multiple moment L, which I showed in the previous slide. And the y-axis is what is called this is the temperature fluctuation or the power spectrum, because temperature related to how much power it has in that particular band. And so you see this picture. The blue line is the theoretical prediction, and the red points are the data points. So they see the match very well. Okay, the theory and the experiment, they match pretty well in this whole spectrum, except for this low multiple moments. And you can also translate that directly into an angular scale in the sky. So this is just a very simple formula. It's pi divided by the L will give you the angular scale. So if you're talking about multiple moment 2, that means it's 90 degrees. Like you're looking at 2 points in the sky, which are 90 degrees apart. Okay. And I mean, that's the largest angular scale that you can have. You can have the what's called the angular correlations. And then if you go to, for example, L equal to 10, that will correspond to 18 degrees in the sky. And then if you go to 180 here, that will correspond to angular scale of 1 degrees. Okay, and so on. Okay, so it's just pi over the L will give you the angular scale. So that's a useful thing to just remember. Okay, and then so here is just a small cartoon which shows that how this power spectrum gets translated into that picture that I showed earlier. So if you go to if you increase this multiple moment, which is on the x-axis here, that's basically getting this, you move finer and finer structures in that picture, right? If you start with a very very small angular, very small multiple moment, that means you are looking at very large angular scales, and then you only see the bigger structures, right? You see this big blob starting, and then when you go to the higher and higher multiples, then you start seeing the smaller and smaller structures. Okay, and that's what is happening here. And then if you go to very high scale, then again you basically don't see anything because you don't have that much resolution, so it just looks same. So they stop at around 2,500 or something, the angular scale. Okay. So now you have all these peaks here. The one peak starting exactly at 1 degree angle, and then there are like 3-4 more peaks there, and then it just kind of dies off. Okay. So what are these peaks? And these are called acoustic peaks. Okay. You all know acoustics. Acoustics related to sound. And very interestingly, I don't know if somebody actually somebody has looked into this in more details. In the Shastras, we talk about the primordial sound, right? There's Shastra which says that, okay, everything started with this Omkar or Pranam and the Sabda Brahma, right? So I think there's a very nice connection here. This related to this acoustics here, acoustic peaks. So let me try to explain what these acoustic peaks mean here. Okay. Again, this is something that could be of interest for future research. I don't know if somebody has looked into it already, but this could be very interesting. Okay, so let me try to explain what that acoustic peak is. So try to think of like some kind of like a mouth organ or something. You're playing a mouth organ, and then what do? You push air into one part, and then and then air goes to the other part, and then it produces the harmonics, right? That's how you get all these nice tunes. And how do you do that? You push the air, and then the air gets compressed and rarefied, and then the sound that goes, so it can either form what is called this the fundamental wave. This is like the half wavelength, or you can form like the first overtone, the second overtone, and so on, depending on how many compressions, rarefactions you put. So with how much intensity you blow into the mouth organ. So that's how you generate the sound, right? This is true for all wind instruments, the flute, mouth organ, what else? I mean, whatever you can think of, all the wind instruments, they generate sound in this way. Okay, the exactly same thing is happening in this early universe. That's why I call it cosmic symphony. Now just replace this length of this tube of the mouth organ with time. Okay, because we know that space and time are interrelated. So just replace this length with the time. And this time is now coming from the very early universe inflation to all the way to this period of what is called the recombination, where the CMB is being emitted, right? That's the period when the neutral atoms form. So what the inflation does, it pushes out everything, right? And then you basically, it's something like very similar to someone blowing into this mouth organ, right? You're just producing these compressions and rarefactions in the air, and here you're doing the same thing in the space. You are compressing and rarefying the space itself. Okay. And you have this hot and cold spots. The red means this is like this is the hot region, and then this red means it's a cold region. Here again, you can also generate this fundamental and all the higher order harmonics, just like you did for the mouth organ, right? So what happens is that you produce the fundamental will be just like one hot spot there and one cold spot there, just like a dipole, right? You produce like one hot spot and cold spot. And then you can generate like a higher modes. This is a quadrupole, and you can have one cold spot, hot spot, cold spot, hot spot, and so on. And then you can do higher peaks and so on. So it will basically scan over all these multipoles in this way, right? So that's essentially what those peaks correspond to. The fundamental one is corresponding to the 1 degree thing there, and then the higher ones will correspond to the other peaks. Okay, and after some time, this will die out because is kind of gets damped. The oscillation gets damped over time. So then you don't see the other peaks there. Okay. But the thing is, it's not as simple as that. There's a little bit more complication because you now add matter into it. Then there'll be interactions between this photon and the matter. And this picture tries to explain that. Again, I don't have much time to go into all the mathematical details of this, but just seeing it. So here you have all these different atoms. So they are also in this hot and cold regions, right? And if something is in the cold region, then you can condense them more than in the hot region because the kinetic energy would be less in the cold region. So from all these particles, they kind of fall into this cold trap. And this trap, so if you have some dark matter in the early universe, then this trap, it gives you this gravitational well where all these particles can fall into. And that's what produces all the structures basically in the universe eventually. Okay.
I hate to interrupt, but if we could to stay on time to get on to the next talk fairly soon.
Okay. So how much time do I have?
It's time now.
Okay. Okay. So I'll try to finish maybe another couple of minutes. Is that okay?
A couple of minutes is okay with me,
Okay.
unless the supreme organizers object.
Okay. Okay. Yeah. So basically, yeah. So that's how you form this the different structures in these different valleys, and then this CMB is going through these valleys, and then it gets scattered, and that's how you get all these different peaks, right? So when the CMB is going through one of these valleys, you get one peak, you get another valley, you get another peak, and so on. That explains these different acoustic peaks. Okay, so now in coming back to the big picture, so this is the outcome of that map. That we know that what is called the cosmic energy, the pie chart. I think Dr. Prabhu probably also showed that in yesterday's talk. So this is the standard model of cosmology. We have only 5% of matter that we see ordinarily. That the rest is dark. Part of it is dark matter, and then 68% is like dark energy. And this dark energy corresponds to lambda, cosmological constant, and this CDM corresponds to the cold dark matter. That's this 27%. Okay. That's the rest of the universe. Now, if you change any of your parameters, then this power spectrum changes very, very dramatically. So that's how you measure these parameters to this 4.9%, 26.8%, and so on. That you get from this varying all these parameters and seeing what value it matches the experimental data. Okay. Now, I mean, so far this is very consistent, very successful, and so on. But there are certain anomalies. Okay. And again, I don't have time to go into all the details, but here I'm just trying to list some of them. Now, if you look at this power spectrum very carefully, you'll find that there are like cold spots and hot spots. They are kind of separated. So one is in the North Pole versus South Pole. So you can see this cold and hot spots, kind of distinctly separated. So that's a mystery. Nobody knows why that is so. And also there seems to be a separation of power for the large angular scales or the small, the multiple movements. And here is just a number. The observed value is like 299.5. The expected should be 1150. So that seems like, quite significant. And of course, including the error bars. So it seems like below what is expected. So that's the mystery. That's one of the anomalies in CMB, which we do not know how to solve at the moment. So one possible solution is through this idea of ellipsoidal universe. So what does an ellipsoid mean? It basically means that you have like a major axis and minor axis. If they're not equal to each other, then it is not a sphere, right? If they're equal to each other, it becomes a sphere. But if they're not equal to each other, it becomes an ellipsoid in 3 dimensions. And then you can measure this amount of ellipticity by this parameter called either ellipticity or eccentricity. It's just the ratio. You take the ratio of these two axes, the lengths, and then take square root of 1 minus the ratio square. So it can be either one way or the other, depending on which way is longer, which way is shorter. It's called prolate or oblate. And this, what it does, it feeds into your metric. Okay. Again, I don't have time to go into the details of the metric, but there's the metric that we use is called FRW metric. But now, because if you have this eccentricity, that will feed into this metric, and it will make these two terms different. So it distinguishes the two directions of space from another direction. It's no longer spherically symmetric. Okay, and that will feed into this quadruple anisotropy, and you can play with all the data, and so that there is actually, you can explain this anomaly in the quadruple movement if I have a small eccentricity, and that eccentricity is just 0.0067. It does not change anything in the higher, the acoustic peaks or anything there, but in the large scale, it does change things quite a bit. Okay, and that's how you can explain some of these CMB anomalies. And then the last thing I want to mention is about the, well, maybe I don't have time, so I won't go into that. I'll just skip that. So yeah, so I think I'll stop there. So I'll just mention at the end that there is growing evidence from these CMB anomalies that that the universe is actually ellipsoidal, not spherical, and that seems to be consistent with the you know, the scriptural view that we have an X-shaped universe. So that's all I want to say. Thank you.